In this part, I will explain the mathematical derivation of the coilover motion. Coilover shock absorber can be modeled as a mass spring damper system. The spring provides a restoring force, while the damper provides a retarding force to reduce the oscillation. In this model, the displacement from equilibrium is represented by xt. The mass, spring constant, and damping coefficient are represented by m, k, and b. Since the spring is assumed to be at equilibrium length, the weight of the automobile is ignored. There are two main forces acting on the coilover. The first one is the spring force. It acts opposite to the displacement and tries to bring the system back to equilibrium. The second one is damping force. It acts opposite to the velocity and reduces the motion of the coilover. Here, x prime represents velocity, while x double prime represents acceleration. Using Newton's second law, the total force acting on the coilover is equal to mass times acceleration. So, the spring force and damping force are combined to form the equation of motion. After rearranging the terms, we obtain the governing second-order ordinary differential equation for the coilover. This equation is second-order because it contains acceleration, and it is homogeneous because there is no external force term. To solve the differential equation, we assume that the displacement has an exponential form. This method is suitable because the derivative of an exponential function is still an exponential function. After substituting the assumed solution into the governing equation, we obtain the characteristic equation. Then, by solving the characteristic equation, we get the general roots. These roots are important because they determine the type of motion of the coilover. The type of motion depends on the discriminant in the general roots. If there is no damping, the system is undamped and continues to oscillate. If the system is underdamped, it still oscillates, but the amplitude decreases with time. If the system is critically damped, it returns to equilibrium as quickly as possible without oscillating. If the system is overdamped, it also returns to equilibrium without oscillating, but more slowly. These four damping cases will be used in the next part to simulate the displacement time graph.
For the constant, we choose the mass equal to 2.729 kg and the spring constant equal to 5.153 Newton per meter. And then we calculate the damping coefficient, B equal to 2 sub mk, and we found the damping coefficient equal to 7.50001 Newton second per meter. So for the undamped system, the damping coefficient equal to 0, and so we can substitute the mass and the damping coefficient and also the spring constant into the second order ODE equation, and then we can find its root using the derived equation. And then we found that the roots equal to a complex number, and then we can find its constant value a and b using the initial condition, and then we can find its final general solution, where we can use the Excel and we use the time start from 0 to 15 seconds, and then the graph is a cosine wave shape with a constant amplitude. For the underdamped system, the B is bigger than 0 and smaller than the damping coefficient, and we choose the B equal to 2.125, and we find the general equation. And the graph shape is a cosine wave, but its amplitude is getting smaller over time. For critically damped, the B equal to the damping coefficient, where the B equal to 7.50001, and we found the general equation. And the graph, the displacement is decreasing rapidly over time. For overdamped, the B is bigger than the damping coefficient, and we choose the B equal to 20.125, and we found its general equation. And for the graph, the displacement is decreasing over time, but it decreases slower than the critically damped. And this is the graph that have all the four systems inside.
So, I will now continue for the discussion part. Firstly, for the undamped. So, what this means is there is a spring but no shock absorber to control it. So, for the right experience, if the car hit a single bar, it will bounce up and down endlessly at a constant amplitude. So, why this is bad is because energy is never dissipated and the car becomes a rolling trampoline. So, this completely destroys a tire traction and make a steering impossible and will instantly cause motion sickness. Okay, so now for the underdamped. So what does this mean? The shock absorber is too weak or severely worn out. So the right experience, when the hitting a bump, the car deflects, snap back past its original position and undergoes several smaller bounces before finally settling down. So why it is bad is because this causes a floaty, unstable ride, or also known as a boat ride. So the continuous secondary oscillation means the tire are constantly changing their load on the asphalt and reducing grip and passenger comfort. Okay, next for the critically damped. So what does it mean? The mathematically perfect balance of damping, which when in the right experience, when a car hit a bump, the suspension compressed to absorb the impact and then smoothly return to its original equilibrium ride height in the shortest time possible without a single extra bounce. So when it is ideal, it ensures a cabin stabilizes immediately, preventing passenger discomfort while forcing the tire back into firm contact with the road for maximum traction. Okay, lastly for the overdamped. So what does it mean? The shock absorber is excessively stiff or dialed up too high. So the right experience, the suspension resists moving freely. When a car hit a bump, the fluid inside the damper moves so slowly that the suspension takes a very long time to return to its original position. So why it is bad? Because the shock absorber is too rigid, so it fails to absorb the impact. Instead, the force of the bump is transferred directly through the chassis and its spine. The ride feels incredibly harsh, stiff and jarring.
And this is the summary compression.